Welcome to the mini lecture Tomography 202. In the previous video, Tomography 201, we saw that sometimes pixel-based methods are the best option for image reconstruction in X-ray tomography. But how do they work? Let me explain a little bit about them using the simplest possible example. So here is today's patient undergoing X-ray tomography. It's a square-shaped, two-dimensional target with 4 internal organs that are also square-shaped. We send an X-ray through our target and use an X-ray camera to record what happened. When we apply certain logarithmic calibration to the camera pixel value, we can actually think that our X-ray data is summing up the numbers in the row inside our 2x2 simple target. So 2 plus 6 makes 8. Another X-ray gives 9, which is 2 plus 7, the numbers in the second row, and then we turn our tomographic device and get 2 more measurements, 4 and 13, as the column sums of our target. So this is actually the direct model of our measurement, and this is the inverse problem. We know the measurements, but the internal structure of our target is unknown. Can we find out what are the real numbers inside our target? Well, it seems to be difficult because here you see 2 different patients that have exactly the same data. Well, there is something weird about this -1 there, because it would mean that the X-rays get stronger inside that area instead of getting weaker. So that's kind of not possible, so we can discard this alternative target, but there are more. Look at this one. Again, it gives exactly the same measurements, although it's a different target. There is non-uniqueness, but where does this come from? The reason is the existence of so-called ghosts. Ghosts are non-zero targets that give a 0 measurement, because then we can just add a ghost to our target and get another target that has the same measurements. To understand where this comes from, we can build a matrix model. This is actually at the core of pixel-based tomographic methods, building a system matrix. So here, the first X-ray we considered, going through the top row of pixels and gave 8. So now we give variable names to our unknown pixel values. x1, x2, x3 and x4, as you see here. And now the first measurement is modeled by a row of a matrix multiplying a vector of our 4 unknowns. And the result should be 8, because that's what we measured. Another X-ray gives another row in the matrix and another element in the measurement vector. We continue. Now look at this new row in the matrix. There are 1s and 0s, assuming that the side length of the small square is equal to 1. And finally, our last X-ray. So now we can call this matrix A. The vector with 4 unknown elements is X. And AX equals M, where M contains our measured and calibrated values. So now we can see by analyzing this 4x4 matrix that it has a non-trivial kernel, meaning that all vectors of the form t minus t minus t t, where t is a real number, will all be mapped to 0 by this matrix. That's where the ghosts come from the kernel of the measurement matrix. So we have this non-uniqueness in our inverse problem. Can we ever solve it? Well, we can, using regularization, which will be the topic in the next videos of this 200 series. Now please go ahead and subscribe the Professor Sam channel and click on notifications so you won't miss the next videos in the Tomography 200 series. See you later!